Hi everyone, welcome back. So in the previous part of this video, we had looked at the foundation for the Gaussian algorithm, which are the elementary row operations. And if you remember, what the elementary row operations are basically what we can do to the rows of a matrix to manipulate it and change it to try to get it into reduced row echelon form. And as you can see here, we went over the three elementary row operations, which were adding multiples of rows to other rows, multiplying a row by a non-zero constant, and swapping rows in a matrix. So what we're going to do is now that we've gotten a grasp on the elementary row operations, these are going to form the foundation for how we can apply the Gaussian algorithm. And we're going to do this by solving a system, which I've written here on the board, and we're going to turn this system into a matrix. And then we're going to learn the Gaussian algorithm by actually applying it on the matrix for this system and solving this system. So the goal of the Gaussian algorithm then is to apply the three elementary row operations in a systemic series of steps to reduce the matrix to RREF. So as you can see here at the bottom of the screen, I've listed the steps of the Gaussian algorithm, which we're going to apply to solving the matrix form of this system. So first, let's go ahead and get these equations into a matrix form. So the way we can do that, to write this guy as a matrix, the way we can do that is we're going to take the coefficients of x1 from each equation in the system, and that's going to be the first column in our matrix. So in this case, that would be 1, 2, 0. Next, we're going to do the same thing, only with the coefficients for the x2. So in this case, you can see that 0, 2, 1, 0, 2, 1. And then lastly, we'll fill in the coefficients of the x3, which in this case are -3, 9, and 5. Now, once we've written in the coefficients for the variables, next we have to include the constants of the equation. So in the equation, we just write an equal sign, and then on the left side we have like all of our variables and coefficients, and on the right side we just have the constants. When we write that in matrix form, what we do is we write a straight line here. And on the right side of the straight line, we can just write in each constant. So that would be 8, 7, and -2. All right, so that's the system written in matrix form. So now let's actually apply the Gaussian algorithm to this matrix. So let's look at the steps. First, we're going to start with the leftmost non-zero column. So in this example, looking at our columns, what we can notice is that we can start with this first column. So we can we can see here, our leading entry here in this first row of the first column is 1. And you can see here from steps 1 and 2 that these two are going to be pretty much interconnected with each other. So step 1 and step 2 are both going to be probably like performed almost at the same time in a way. Because what's going on here is that, like, let's say instead of a 1 here, we had a 0, for example. Then in that case, when we go to start with step 1, we would have to pick still pick the first column as our leftmost non-zero column. But what we would do is we'd have to start with the second row because the other entries are 0. And that's where step 2 comes in. Because what we want is we want this row with the first non-zero entry to be at the top. So that's when we perform that row swap. So like let's say in this case, like let's say this actually was our matrix here as I've written it. So then what we'd want to do is we'd want to swap row 2 and row 1 in order to get this non-zero 2 up at the top. Now, of course, in our actual matrix, we don't have a 0 there, we have a 1. So at this point, we can just start with the first column and the first row, and we don't have to worry about step 2 in this case. So we don't have to worry about that row swap. So, okay, so at step 1, we're looking at the first column, and the first row. So at step 3, which says add or subtract multiples of the first row from all other rows to make zeros below the top entry. So in our case, what we want is to have zeros below the 1. So like we don't want this 2, for example. We want to get that 2 to become a 0. And as you can see in the last entry below the 1, that's already a 0. So we won't have to mess with that one. So it's just a matter of getting this 2 to become a 0. And that's where the elementary row operations come into play. Because like as you can see from the steps of the Gaussian algorithm, it says to add or subtract multiples of the first row. And if we go back up to the elementary row operations, we can see that our first operation that we defined was when we can add multiples of rows to other rows. So how will that actually look in practice? So let's write our matrix. 1, 0, 3, negative 3, 2, 2, 9, 0, 1, 5, and then we have 8, 7, negative 2. So how this is going to look is that since remember our goal is to make this 2 a 0. And we can do that by subtracting a multiple of the first row from the second. So how that will look in notation, we're going to have row 2 minus, and the particular constant that we pick, we would determine that from seeing like the relationship between the first and the second row, like these entries in the first and the second row. So like we can see that 1 times 2 would get us the 2 that we need. So in this case, what we'd want to do is subtract 2 times the first row from the second row. And then we're going to put that back into row 2. So at this point, our first row will remain unchanged, as will our third row. And then for this, the way the second row is going to look is we're going to think about saying 2 minus 1 times 2, because remember, we're looking at 2 times the first row. So it's 2 minus 1 times 2, which is just going to be 0. Then we're going to think about 2 minus 0 times 2, which of course will just, 0 times 2 is just 0. So it will just be 2 minus 0. And so then that will give us 2 in this position. And then lastly, we're going to be thinking about doing 9 minus negative 3 times 2. So that would be 9 minus negative 6, or 9 plus 6. And then that will just give us 15. And then on the constant side, we're going to be thinking about doing 7 minus 2 times 8, which will just give us negative 9. All right, so at this point, we've gone step 3. We've completed step 3 because we have all zeros here below the top entry, which is what we wanted. So step 3 is now complete. All right, so let's look at step 4. All right, for step 4, we're going to repeat steps 1 through 3 for the remaining equations. So what that's going to look like is, so just like how we wanted zeros below this leading entry here, we're going to do the same thing over here in the second column. We're going to want to take this, 1, and we want to make that a 0. And if you look carefully at this matrix, one thing we could do maybe to try and make this a little bit easier is we could go ahead and perform a row swap at this point. And the reason why this will make things easier is because if we put row 3 in row 2's position, then that'll help us to avoid fractions. Because when you're doing these elementary row operations, it's usually a good idea to try and avoid fractions where possible, just to try and keep things as simple as possible. So if we go ahead and write that back in, we're going to, again, remember we're swapping row 2 and row 3, and then that will just leave us with this result. And now, at this point, we can go ahead and 0 out this 2, because that's, again, remember we want to have all zeros here below this leading entry. And we can do that by we can do row 3 minus 2 row 2, and put that into row 3. And then that will leave us with 1, 0, negative 3 on the top. Again, that's going to remain unchanged. And our second row will also be unchanged. And in the bottom, again, just doing that, applying that row operation, we're going to just be left with 0, 0, 5, negative 5. Now at this point, after this step, you'll notice that our matrix is in row echelon form, the REF form. But ultimately what we want is reduced row echelon form, our REF. So in order to do that, we have to complete 2 more steps. And you can see here, we have them listed here, steps 5 and 6. So for step 5, we're going to start at the rightmost pivot. And now remember that the pivot means the first non-zero entry in the row. So in this case, that would be our rightmost pivot would be the 5. And we want to obtain zeros above each pivot by adding or subtracting multiples of that row from the rows above. So basically what we want to do is we want to zero out this 5 and this negative 3. We want all zeros above this pivot in this last row. So if we wanted to do that, we could go ahead and do some more elementary row operations. We could do row 2 minus row 3 and put that back into row 2. And then that will leave our matrix as 1, 0, negative 3, 8. And we'd have 1, 0, or 0, 1, 0, 3, and 0, 0, 5, negative 5. All right, at this point, I'm going to need to create a new page. That way we have room to work. All right, so at this point, notice that we've gotten rid of that 5 and we've got a 0. Now we've got to zero out this negative 3. But as you can see in this current form, the way row 3 is currently written, well, that means we'd have to deal with some fractions. Let's see if we can try to avoid fractions, right? So let's go ahead and apply that the second elementary row operation, which is when we multiply a row by a non-zero constant. Let's do that to row 3 and get this so that way our first entry would be a 1. So if we do 1/5 times row 3, put that back into row 3, that will just leave us with 1, 0, -3, 8, 0, 1, 0, 3, 0, 0, 1, -1. Now, doing this step had the advantage of zeroing out this -3 a lot easier. Because now you can see our next step would just be we could just add 3 times row 3 to row 1 and put that back into row 1. Which would ultimately just leave us with 1, 0, 0, 5, 0, 1, 0, 3, and 0, 0, 1, -1. Alright, and now we have one more step to go. That's step 6. Make all pivot positions 1 by dividing each row by the value of the pivot in that row. So in this case, with step 6, we already have all of our pivots are 1. Because you can see here, we have a 1 here, another 1 here, and then a 1 in the third row. So the other advantage here when we took this step, when we multiplied row 3 by 1/5, this actually helped us to accomplish step 6 because it formed a 1 in the pivot position in row 3. So ultimately we've already completed step 6 at this point. And as you can see at the conclusion of all these steps, we finally got the matrix into reduced row echelon form. Alright, great. So now at this point, all we have to do is just read off the solutions to the system that we were trying to solve. So the way we do that is we remember that each of these columns is representing like the coefficients for each variable. So as you can see here in this first column, we have a coefficient of 1 on the x1. We have a coefficient of 0 on the x2 and a coefficient of 0 on the x3, and that's equal to 5. We have, and then similarly continuing down the rows, 0 times x1 plus 1 times x2 plus 0 times x3 is equal to 3. And then lastly, 0 times x1 plus 0 times x2 plus 1 times x3, and that's just -1. And simplifying this down, we just get to x1 is equal to 5, x2 is equal to 3, and x3 is equal to -1, and this is our solution. And that's how we can apply the Gaussian algorithm to get a matrix into reduced row echelon form in order to solve a solution of linear equations. I hope that was helpful. Thank you for watching.